right, so we are getting close to finishing up at least the initial wave of power amplifiers that we'll look at before we get to some more advanced stuff. So we're going to finish up power amplifiers hopefully today, maybe start on mixers depending upon how things go. And then we'll do mixers, we'll do VCOs, and then we'll start covering a few more advanced topics in RFICs. I want to get the mixers and VCOs first so that you have people that are doing those on their projects have at least a little bit of coverage. Okay. So when we were last week, we were looking at this concept of the, sorry, wrong page here. We were looking at the concept of the class F amplifier, and the class F is, pretty much just a brute force way of realizing a switching amplifier with 100% efficiency. But we did look at this concept that if we only terminate, and the way that we of course do that is we terminate all the odd harmonics with a high impedance, all the low harmonics with all the even harmonics with a low impedance. And if we do that, then we get 100% efficiency. But if we only terminate a few of them, we can do pretty good. For instance, if we terminate 1, 3, and 5, and 1, 2, and 4, or I guess I should just say 1 through 5 from the harmonics, we would get a 91% efficiency. So it's not too bad. Okay. So there's this other concept from Grebennikov that I'm going to show you now on making a class F power amplifier. So, if we just recall from just a moment ago, that if we only terminate the fundamental plus the second and the third harmonic, then you'll see that the drain efficiency is 82%. Okay. So we can do this with just a 3-element network. And we'll have the conditions that Z1 is equal to Z3 is equal to, I'll say infinity, but just some high impedance, and Z2 is equal to some low impedance, I'll say 0 here. And Grebennikov has 2 networks that do this. So the one network he calls the parallel circuit. And it looks something like this. Okay, so there's still some matching network that's converting the antenna impedance down to the optimal termination impedance for a class F amplifier. But then he has these extra 3 components that are going towards the supply network. And he tells us that L1 is equal to 1/6 omega naught squared times C drain, where C drain is the drain parasitic capacitance. L2 is equal to 5/3 of L1. And C2 is equal to 12/5 of CD. Has anybody ever seen the Zverev? There's a filter book by Zverev, which is just filled tables full of how you make different filters. I often feel like some of these Russian guys, they were just stuck in the gulag or something like that, and they just tried every possible combination of things to make it work. Grebennikov seems much smarter than that, but I don't. Anyhow. Of course, the way that things are going with academic freedom on U.S. campuses, we might be in a similar position here sooner or later. All right, so this is the series circuit. Now, what's kind of interesting is these are nomenclature that he provided, but you can see that I suppose the parallel circuit, there is only one truly, purely parallel LC network. And in the series network, there's only one truly resonant network, L2C2. So you can see where, this is the series network and this is the parallel network. But obviously both of these are a combination of series and parallel components. So don't get confused by that nomenclature. So we have L1 in this case is equal to 4/9 omega naught squared times CD. L2 is equal to 9/15 times L1, and C2 is equal to 15/16 times CD. I argue that if you look at these, the series circuit is a little bit better. Why would I say that? In the context of RFIC.
The series one you said is better?
Yeah.
Yeah, the inductor is L1 is smaller.
I would say both inductors in general are a little bit smaller.
Yeah, L2 is smaller.
All right. In either case, these actually still aren't great. I have two inductors for both of these that I'm going to add in addition to whatever I add for my matching network. Now I can probably try and fold that impedance of that network into my matching network somehow, but it's going to be a little bit tricky. All right, so much like the Class E network, we don't have a lossless switch. So the model for our switch is we have some resistance in series with an ideal switch that also has some parasitic capacitance associated with it. So we have a switch with a resistance R switch and some parasitic capacitance in parallel. All right, and we can calculate what the power lost in the switch is. It's equal to P out times 2 times R switch over R opt. And then we can figure out what our modified version of R switch is. We're basically, if we're trying to size a power amplifier to give us a certain amount of output power, we have the original equation for a class F amplifier, 8/pi squared times VDD squared over P out. And if we want to adapt for the fact that we have loss in the switch, we can subtract 2 times switch. And then ultimately, we can also account for the efficiency in the class F network. Efficiency, if we include switching loss, is equal to 1 minus 2 times R switch over R opt. Now we can start folding in things from non-idealities from the switching loss. Of course, the total efficiency is the product of really all of the different losses we might have in the circuit. So we just found the switching loss. We might have our suboptimal class F waveforms. So in other words, we only terminate a few of the different harmonics. So we have a factor in there for that. We have our matching network losses. So our total efficiency ends up being a product of all of these losses. And I should also add that if we have a capacitance in our drain network, we can't operate as a class F to all frequencies. So much like there was a limitation on that modified Grebennikov class E network, there's actually one for all class F networks. And the maximum operating frequency is going to be 0.47 over R opt times C out, and this basically just ends up having to do with your ability to shape the waveforms if you have a drain capacitance. Sorry, this is drain capacitance. C out. Okay, one last thing on class F. I did mention the other day, there is the concept of inverse class F, and really all of the amplifiers that we've seen, there's an inverse version of them for the switching networks. And the inverse version is really just that we're going to shape the waveforms a little bit differently. So we have a class, you might see this in the literature, class F inverse. We're going to square the current waveform and half rectify the voltage waveform. And if we do this, the math ends up working out very similarly. We can find our fundamental voltage waveform. It would end up being pi over 2 times VDD. Our fundamental current waveform is going to be 4 over pi times VDD. P out is equal to V1 times I1. And then we can find the impedances at the different harmonics. So the impedance at the fundamental, Z1 is equal to V1 over I1. This is equal to R opt for the PA. And this is equal to pi squared over 8 times VDD over ID. R opt is equal to pi squared over 8 times VDD squared over P out. All right, what can we say about this compared to our other switching amplifiers that we've seen so far? It's true. It's true. All right, pi squared over 8 is definitely better than 8 over pi squared. So it's better than the class F. Class E was 0.577, so this is better than that. It's not quite as good as the Grebennikov class E, the parallel circuit. So, you know, one challenge that we have is when we make, in particular, when we make CMOS amplifiers, we can make the current go arbitrarily high. We can make the devices very wide, but we don't like to have the voltage waveform go arbitrarily high. So here we have the potential to have the voltage waveform peak fairly high. So we have to look out for that. Now, slightly different than the class F network, all the odd harmonics are going to be terminated with a short circuit. All the even harmonics are going to be terminated with an open circuit. And that's how we create the inverse class F. So it's basically everything that we did for the class F network, we do the inverse for the inverse class F network. All right. The inverse class F design example that we might have, if we just wanted to terminate a couple of harmonics, we might do something like this. So this network is tuned to 2 F naught. This network is tuned to F naught. At higher frequencies, or at high frequencies, C1 and C2 are low impedances. And the second harmonic sees a high impedance due to the parallel resonance between L2 and C2. So looking into L2, C2, we see that parallel resonant network. So at the first even harmonic, I should say the second harmonic, the first multiple, we see high impedance. Everywhere else we see a low impedance. So this is a suboptimal class F network. And the opposite analysis that we did, that we showed in the prior case, where we had DV, gamma V and gamma I, the opposite of the analysis applies. So all the coefficients that we had for gamma V become the coefficients for gamma I, and vice versa. And you get better results if you terminate the even harmonics and high impedances. So this would be kind of a suboptimal design. Okay, so that's class F and inverse class F. We'll do a homework where we actually do all versions of these switching amplifiers coming up here. It'll be assigned on Wednesday, so we'll get some practice looking at these things. The main thing to think about is just that you're trying to shape the waveforms in order to cause non-overlapping currents and voltages. Yeah.
So just to be quite clear, what you said is a suboptimal design is because all of the even harmonics above the second harmonic are terminated at a short instead of a open.
Yeah. Okay. Well, it's suboptimal because first of all, we didn't terminate every harmonic. In order to,
well, terminated means like they see a small impedance.
Sorry, we didn't terminate every harmonic properly.
Okay.
Yeah. Yeah, in order to do that with class F networks, you tend to have to come up with some type of transmission line network or some type of cube network that manages to do that. Okay, so we've got one last class of switching amplifier to look at. It's called a class D. It might be the easiest of all of the amplifiers conceptually to think about. Analytically, I think it's actually a little bit more difficult than the class F amplifier is, but not too much. Now, one of the things that you'll notice in the literature is that people try and come up with names for power amplifiers all the time because it's the quickest way to fame and fortune if you come up with a new class of amplifier. But it doesn't necessarily mean that everything that you come up with is true to the definition. So case in point, there are a few amplifiers, and we might talk about them later on in the class. There's one called a class G. That's where I use a supply modulator in the network. There's that's a discrete supply modulator. So I have a supply modulator that might have steps in it. So might step from 1 volt to 2 volt for the supply voltage and so on, depending upon how big the envelope is. There's one called class H, which would be if I had a continuously adaptable supply modulator, so I could continuously adapt the supply voltage that's being provided through the PA. There's one called a class J. That's one where functionally the math shows that it does everything that a class B does. It just does it with slightly different termination networks. This is where we start to get into the murky waters of power amplifiers, where if you want to call it a new class of PA, fine. I just look at it and say you just kind of reshape the class B waveforms a little bit. I don't know what you're really functionally doing. It is a new network, so that's good. Later on, there was one called a class O. Anybody care to think about why you might call a power amplifier a class O? They used a PMOS and an NMOS transistor in their power amplifier. And since the letter O is between P and N, now that got published at ISSCC. That's the premier circuits conference in the world. So, you know, sometimes it pays to be audacious. All right. I suppose because we do have a PMOS in it. Yes, this is a class.
An NMOS and a PMOS.
Unfortunately, class D already existed. In the class O, they were technically using the transconductances of both devices, whereas this is a switching amplifier. So, in general, though, I just want you to take that when you're making a linear power amplifier, linear just means that we're using the device as a transconductor for some portion of the conduction cycle. So we're using the GM of the device. And when we're looking at switching amplifiers, we're just turning the device on and off and pulse shaping. And those are the fundamental basics of the power amplifiers. Another thing that does happen is if you look at RF amplifiers, they might have slightly different names than their lower frequency analog counterparts. So for instance, the class D, we're going to see in a moment, is a switch with a series resonant filter. If we made that filter instead of series resonant a low pass filter, that would be what people in the analog or in the power electronics world might call a class S amplifier. And then class D in the audio amplifier world would be a low pass filter instead of a band pass filter. So the names do get mixed up across the different circuit domains. All right, so here, class D, just what I said, it's a CMOS inverter in our case with a series resonant network. Now, it could be something other than a CMOS inverter. For instance, when it was invented in the 1960s, there were no CMOS transistors, so we know that it could not have been a CMOS inverter. But nonetheless, the concept, I think, works best with this inverter. So here we have our CMOS inverter, and then we have some LRC network. Where the series resonant network is tuned to F switch. So F switch is just whatever our switching waveform is, the frequency of our switching waveform at the input. So we have to figure out what the operation looks like. When the PMOS is closed, we have a sourcing current that's sourcing charge onto this capacitor. This capacitor is going to be charged from 0 up to VDD. And this is going to happen over the range of time from 0 to pi. So we're just doing this in radians, so half of the cycle. So if we look at the drain voltage, ultimately this should just get kind of squared up. And then at time pi, the switch, the PMOS is going to open, the NMOS switch is going to close. We have our same network. Except now we're going to have a sinking current that's going to discharge the cap. So the cap is going to go from VDD back to 0. And if the switch is relatively low loss, this should happen quickly, so we should have a square-like waveform in the voltage. Now, fundamentally, if we look at the output waveform, we're only allowing ideally, we're only allowing the fundamental frequency to pass through the series resonant filter. So the output should just look something like a sinusoid. And you can ultimately show that the drain current is going to become half rectified just due to this charging discharging operation. So we're not, during that first part of the cycle, we're only putting current towards the load. It's not going to ground, and then during the second half of the cycle, we're going to dump all the charge back to ground. So we only have current flowing through the drain from that second half of the cycle.
I mean, the drain of the NMOS.
Yeah.
Yeah, you just don't, you're not talking about PMOS. I mean, it'll have.
Well, we don't have any current going. You know, ultimately, what we're trying to keep track of is how much current is going from from the supply to ground. Yeah. Okay, we can describe this mathematically a little bit better from those waveforms. So from 0 to pi, the PMOS transistor is on, the NMOS transistor is off. Our drain voltage waveform is VDD minus any switching resistance times any drain current times the sine of omega naught of t. And our drain current is equal to 0. This is the NMOS transistor. Our output current is equal to ID times sine of omega naught of t. During that second half of the cycle, the PMOS turns off, the NMOS turns on. Our drain voltage is now 0 plus our switch times ID times sine of omega naught t. ID is now equal to ID times sine of omega naught t, and I out is just the opposite phase of that. Okay. Okay, the resonant circuit ideally filters all but the fundamental current, so that's the only current that can flow to the load. So from these waveforms now, we can find what the fundamental voltage and current waveforms, or what the components of the fundamental voltage waveform is, and ultimately what the DC current and DC power are. So to find the fundamental voltage waveform, Fourier analysis, just like in the other amplifiers, 1 over pi times the integral from 0 to 2 pi dd times sine omega t dt. This ends up being equal to 2 over pi times VDD minus ID times R switch. So here we're actually starting to, in the analysis, we're taking care of of any loss that we might have due to a switching resistance. Nominally, the switching resistance is 0 if it's an ideal class D, but in reality, there's going to be some switching resistance. We can find our DC current. It's just the average current, so 1 over 2 pi integral from 0 to 2 pi of I out. Oops. D omega times T. This is equal to ID over pi. And then ID is equal to V1 over R opt plus R switch, which is equal to 2 over pi times VDD over R opt plus R switch. And finally, we can find our DC power, VDD times IDC. Okay. All right, so we have our DC power. It kind of makes sense. It's just it's basically just the supply of the RMS voltage, the fundamental component of the voltage divided by the square divided by the sum of the optimum termination resistance plus any switching resistance that exists. Now we can find our output power. IRMS squared times R opt. Here are substitutions for I out in here. And ultimately, we can show that the drain efficiency of a class D amplifier, P out over PDC, is equal to R opt divided by R opt plus R switch. So interestingly, this is really the drain efficiency. I mean, this is a voltage division. What we're ultimately saying is that if our switch is ideal, we won't divide the voltage across the switch, and you'll get 100% efficient operation. Okay, now we do have potentially lossy passives, so we're going to be doing an impedance transformation in order to produce R opt. We're not going to normally make R opt with just a physical resistor. So we can talk about the loaded quality factor of the series resonant network. So that the network quality factor would be equal to the impedance of the inductor divided by R opt, or it's equal to the impedance of the capacitor divided by R opt. Typically, we're going to realize the impedance transformation with a matching network, like I just said. So what kind of quality factors can we use in reality? Yeah, 3 to 5. So when we want to design a class D amplifier, it's a pretty simple process. So we choose our opt that's going to give us the desired output power, and we synthesize a matching network. Transform 50 ohms to our opt. That matching network in and of itself is already a bandpass network, so we don't need to add a definitive series resonant network. Matching networks, LC matching networks are inherently bandpass. And we said that they might have a shape before, but hopefully you'll recall from the homeworks that when we plotted the frequency response, there was always a bandpass shape that might be favoring one side versus the other. All right. Yeah.
So, sorry, can you explain why the quality factor of the network is so low? I remember many weeks ago, we talked about network quality factors, and I kind of missed the point there. So, like, the inductor could have up to like a 20 quality factor of 20, but why is the network quality factor so low?
Yeah. So let's go back. So we did this little calculation. So we did these calculations that show you what the loss in the matching network is. And it ends up being proportional to 1 minus something over 1 plus something, and we kind of boiled it down really to this main thing that said that the inductor is almost always lossier than the capacitor, so if we have an inductor that has a quality factor that's limited to something on the order of 20. And we have an acceptable amount of matching network losses, then that's really, it might be 80%. We want our matching network to have an efficiency of 80%. That's going to dictate what the acceptable network quality factor is. Yeah. Now, if you've been searching through this 22 nanometer kit, one other thing that you might have noticed is that the quality factor of the inductors 20 is very optimistic, you might have noticed. If you were searching for anything that's in the nanohenry or plus nanohenry ballpark, the Q is probably closer to 10 to 12. Yeah. You can find inductors that have Qs in the 20 ballpark, but there are hundreds of picohenries.
And just to sort of the final thing on this, like, I always have the intuition that a high quality matching network would be the lossless one. But really, I guess what it's saying is if your matching network has a high quality factor, you're storing energy in the matching network instead of transferring it through. Is that the intuition there? It's not intuitive. You're not.
So really, it's that you're not dissipating energy in the network. So Q is a ratio of how much energy you store per to how much power you dissipate per cycle. So it's just saying that every amount of energy that's going into the network is going to be able to be transferred out, at least at some frequency, right? That's what it means. The lower the Q of the components inside of the network, the more loss that happens every cycle. Right. So, and that just gets heat. That gets turned to heat.
Yeah.
So while we were doing the LNA homework, in the tutorials you mentioned, I don't know we talked about this, but the surface frequency of the not considered. Setting 15 gig is minimum operating at 5K or 6K. Is that a rule of thumb that we use with less than 3 times?
Well, let's see. Let me let's make a.
Because that seemed to limit more of the Q than anything else that we've chosen in practice.
Well, Do I not have extra paper around? Okay, that's fine.
Is it that hard to make more virtual paper?
It's not that hard, but I mean, I just did what a paper mill in the past would have taken them, I don't know, some effort. So when we talk about self-resonant frequency, you ideally want your inductor to look like that. That allows you to design for that, at any frequency using that component. But in reality, when we make this on CMOS, because we have parasitic capacitance, the inductance is going to look something like that. In fact, I'm showing that this thing might look capacitive for a while, right? So the challenge that you have is you need to operate at some frequency, right? So you're trying to operate at this frequency. The closer you get to this slope, and the higher the quality factor, the faster the rate of change of the inductance is. So if you're trying to make a design and center it, and you're getting yourself close to that slope where you're getting near the self-resonant frequency and the Q is high, you're subjecting yourself to quite a bit of variation in the component, right? That's why you're trying to keep the self-resonant frequency well above the point where you're going to use the inductor. Now, it just so happens that our definition for quality factor, the convenient definition, I should say, is that it's equal to reactance over resistance. And unfortunately, at self-resonant frequency, what do we say happens to the reactance? It goes to 0. The reactance doesn't go to 0. We have a canceling reactance. What is still happening inside of that, inside of the LC, inside of this L circuit that has parasitic C, is energy is still sloshing back and forth between the inductance and between the magnetic field and the electric field. It's being stored in, sloshing back and forth between being stored in either of those. And it turns out that the Q is actually probably peak near the self-resonant frequency, but it's not a Q that we can use. This is internal to that, that component. So things are getting kind of trapped in the component. So, oftentimes we might want to use a component near its self-resonant frequency because it's probably peak Q, but that's also the point where it's very susceptible to PVT variations. It's moving all over the place. Yeah. So as a point of design, I don't do that because I can't control it. If I could control it, it'd be a great point to design it. Self-resonant frequency has to do, so Q and self-resonant frequency, the reason that you don't find a lot of inductors that have a high quality factor in a kit and a high self-resonant frequency is when I make the inductor, if I want a large value of inductance, I do something like this. And if I want to keep increasing the size of this inductance, I might add more turns to this thing, right? So I might so the pink is a crossover where as I add more vias to this thing, I'm going to a lower metal. The lower metal is lossier. I'm getting things closer to the substrate. I might be reinforcing eddy currents that are flowing in the substrate. So I'm getting more loss from the substrate due to these things. And I have more crossover points, so I have more capacitance. So all of these things are kind of counteracting, and that's really why the quality factor that you find is kind of best for a single loop that doesn't cross over.
Just had a question regarding the center top of the inductor. So when you make an inductor, we custom design of the PDA. Why we cannot use a lower metal even for a center top? I know this the downline is lost here, but when you have a center top, it is always fixed, right? It might have some IR drop because of the loss signal or the resistive.
Well, they put so why you can't, if you draw your own inductor, you can do almost anything you want as long as you follow the design rules.
I'm just saying, in literature, we never see people kind of using lower metal layer for.
Well, normally I'm going to be passing a DC bias through that. So if I'm moving to a lower metal, and that's going to have a much larger series resistance, so I'm going to have a larger IR drop on that thing.
Except IR drop, is there any specific reason?
I also am going to get myself closer to the substrate for not necessarily any good reason. I want to avoid being near the substrate if at all possible. Other than my devices, I mean, what you typically want to do in an RFIC is make my devices and then route away from the substrate. Get to less lossy metal as fast as possible. The reason that you don't see them do the center tap on another metal layer in the kit is that they just didn't want to draw a P cell that would do that. They can do it. So if you want to do that, you can do it. You can draw, like I said, anything that you can draw anything that you want to. But as you get closer to the substrate, the metals get thinner, losses get higher. Parasitic capacitance gets worse. Not necessarily a good thing. Okay. All right, so we can add a few more practical considerations for efficiency in a Class D network. And I have a spreadsheet that designs Class D PAs I'll share with everybody, but we have parasitic capacitance at the gate. And compared to the other switching amplifiers, that gate capacitance is bigger. Why is the capacitance bigger? I've got a PMOS plus an NMOS, and the PMOS device is probably going to need to be sized a little bit bigger than the NMOS device if I wanted to have equal resistance, so much bigger capacitance. It's also, yeah.
Say this is the Class O amplifier. You must stand it.
Yeah, I would not say this is a Class O, but it was named a Class D well before the Class O, so maybe that's why they didn't try. So there's power consumption whenever we're switching that gate. This is 1/2 CVDD squared F. I also have a parasitic drain capacitance. Now, in the past, some people have done things to try and tune this out to minimize the loss. So for instance, I could put a network with big cap, and I could put an inductor where I tuned that inductor to the resonant frequency, or tuned L, the square root, 1 over square root of L times C to be resonant with the switching frequency, and that would mean it was a high impedance to ground. So that would prevent some power from going through there. That only works at 1 frequency, and it is big. I need an inductor to do that. Can be done. Our output power is equal to 2 over pi squared times VDD squared over our opt. Our switching power, PR switch, is equal to P out times 1 plus R switch over R opt. And we can calculate what the total efficiency of this system is. So remember, we talked about different concepts of efficiency. Total efficiency is basically output power divided by everything bad. And that's going to be output power over output power plus PCG plus PCD plus PR switch. We can also have crowbar in this one. If the PMOS and NMOS turn on simultaneously for some period of time, they'll dissipate power. And then we can have power in our matching network as well. So now in the design of a Class D network, like I said, we're probably going to use a matching network. So, we're going to do something like a tapped capacitor matching network. So the design in this type of thing is we're going to iterate the device size and the termination impedance until we maximize the total efficiency while meeting our power output requirement. And how do we do this? I just write a giant MATLAB script that takes into account all of these things and uses a while loop and just goes through until the design is solved. Yeah.
So like every professor in every class before this, we said like, don't iterate, just don't do a brute force, design using design principles.
We've given you the equations. I've given you the equations that tell you how to do all the designs. They tell you what direction you should. I'm much more. So first of all, the device model that we give you is not a true model. And so we can use it to do basic CAN calculations, but ultimately we're going to have to use some tool. My method is a tool that I wrote out in the tool what each of the contributions to the loss is, and then iterate through based upon knowing what those contributions are. Now, if you ask me how to minimize some aspect of the loss, I'll know from the equations what to do, but my intuition is almost never as good as including all the second and third order effects in my MATLAB script and having it tell me what the size should be. Yeah. I don't ever want especially in fine line CMOS design, our models are so divergent from the physical reality that the point of understanding the square law is just to give us a starting point. But beyond that, it's not much use. If I ask you to find, in fact, on this homework, I'm going to ask you to find the mobility times C product for the device. Now, if I asked you to find that at different bias points, you would tell me a different number for every bias point. So not a very useful metric any longer.
Yeah. Have much to learn in the ways of RFIC.
That's right, young Padawan learner. Okay, let's, speaking of power amplifier design, I did want to open up the simulator real quick and show you something while we're looking at power amplifiers. So that's really kind of it for Class E. I'm going to share the MATLAB that does this optimization, and you can kind of see, I meticulously, I make a model of the device, which calculates the width of the device in order to achieve a certain resistance. So essentially what we do is go through and make a lookup table, which is we sweep the device's bias voltages and keep track of its gate capacitance, drain capacitance, and channel resistance. And from that model, we can then feed that into our calculations for the Class D amplifier and iterate through and tell you what the size of the device should be to deliver a certain amount of power. We're going to use that a little bit later on when we look at switch capacitor power amplifiers, because then we can even make some other inferences, but we'll get to that in a bit. Okay. Let's roll the dice and see what machine. It worked. Okay, I put an example in here for homework 4.1 already. Okay. Now the homework is going to go through and have you calculate what you're going to end up needing to find the maximum current, maximum drain current. So you're going to need to keep kind of increasing the size of the device until the device can provide enough current for you to achieve the output power that you're looking for. I like to add some equations to the mix. So one of the things that that is going to become important for our switching amplifier, for our Class A amplifier, is that we need to kind of go through the full range of voltage and current. But we have a cascoded transistor, so the full range of voltage is going to include some effect from the knee voltage. So. Oh yeah, a couple things while we're looking here. So you can try and save the drain currents to the output, but Cadence sometimes has fun with these. For some reason, sometimes it just doesn't like to plot them. It depends upon the data format that it saves them in. It can be tricky, but Cadence will always provide you the current flowing through the supply. So the drain current in this particular case is really the current that's flowing through this V2 supply. So if you select the V2 minus terminal as an output, that will plot what you might have come to expect as a characteristic curve for a transistor. Let's see if we can. Yeah, so there you go. Now, where is V knee on this thing? Probably somewhere in this ballpark, but you can also say that it's speculative. We do know, though, from the model that we can figure out what V knee is. So we can go to results, results print, DC operating point, and we can grab each transistor, and V knee is also called VDS SAT. And you can see that it's, in this particular case, about 370.5 millivolts. If we want to grab that more permanently, we can go to Tools, Calculator, and use this op, select the device, and then you'll have a list of parameters from the device, we wanted, where is VDS set? Okay, there we go. That will add this to the calculator, and then we can send that to the output using that little sprocket. Did anybody ever watch the Jetsons when you were kids?
Yeah.
I just loved it. I mean, there was Spacely Sprockets and Cogswell's Cogs. They were competing businesses to sell, I guess, sprockets. I don't know. Futuristic. I just changed the variable. So, but one transistor was called N1, the other one was called N0. So I plotted N1 originally, but it stands to reason that N0 also has the same property. And so I can go now back into, where's my simulator? I added these two as outputs. I'm going to call this VOV2. VOV1. And I'm going to add an expression. I'm going to call this VNI. And this is going to be equal to VOV1 plus VOV2. So now I have VNI. And then I can do something interesting. Now let's rerun the simulation really quick. All right. Now, one thing that you can immediately see is that VOV1 is not equal to VOV2. Why is that? The devices are equal. They have the same current flowing through them. The bulk, that's right.
Body bias effect?
Yeah, the body bias is different for both of these, so that's going to make the difference. Okay, we can also, let's go back to our calculator, go Tools, IDC, this, and then I'm going to do value, and I'm going to interpolate at VNI. And this is going to effectively tell me what the current is, the max drain current. Because if I were looking there, so the max drain current we know is happening somewhere around this region because that's where the knee voltage is. It tells me that it's exactly at 642 millivolts in this particular case. So somewhere right around here, and it tells me that the drain current's 250 milliamps. So in fact, we just calculated that a minute ago, but it was somewhere in that ballpark, 200 something milliamps. All right, so you can use the calculator pretty handily to figure a lot of these things out if you kind of play around with it. It's pretty potent. Any questions about that? All right. All right.
Yeah, so the overdrive voltage VOB is VGS minus VTH, right?
Yes.
So those devices also have different VGSs, right? Because
yes,
both
but
of their gates are at 1.8, but their sources are not both at 0.
Yeah.
So that's also contributing, I mean, in addition to what Sean said about the.
Yeah, in this case, the primary difference is going to be yeah, I mean, if I set VGS to a different value, you're going to get a slightly different result. But the primary difference here, in this simulation, we have set both gate voltages at 1.8 volt. So there's a different threshold voltage because of that body bias. And yes, you're right. This upper device also sees a different source voltage. So yeah. Okay. Yeah. And it did go through, calculated it, that the maximum drain current is 293. We know what the maximum drain voltage is. We could go and write some more equations and actually write what the output power is. Now, as you keep increasing the size of the device, the current carrying capability is going to go up, and the overdrive voltage is also going to change kind of slightly due to second order effects. So the easiest thing to do is just kind of sweep the width over length until you get the current that you want. Or you could calculate 1 point and assume that if you double the width, you're going to double the current, and more or less that'll be almost true.
I never had very much success with that.
Yeah, it's
well, maybe with the width and the current with other stuff. I think that's a pretty linear relationship.
It should be fairly linear. Okay, how much time do we have left? All right, so we're not going to start mixers today because we'll just, we'll kind of maybe.
Hello, Professor. Can I ask one more question regarding the homework?
Yeah, absolutely.
So in the question, it's mentioned, I think 24 dB power.
Yep.
So is that the minimum or the maximum? Because I thought it was maximum.
So we'll call it the minimum power in this case.
Got it. So design anything above that, basically, or around that? Does that make more sense?
I wouldn't go too far about it. So what's going to happen is if you try and start getting a lot more output power out of the device, you're going to have to make it really, really big, and then you're going to get diminishing returns. The reason that I said it's the minimum power is, in reality, in the next part in problem 2, you're going to be designing a power amplifier with that power transistor. In any real power amplifier, you're going to have matching network losses, you're going to have current division, all those negative things. So if you just design the power cell to be able to to just barely provide 1/4 of a watt, which is 24 dBm, you're probably going to have a very hard time actually achieving 24 dBm because you have all these losses you didn't account for when you size the device. The device needs to be able to produce the power that you require plus any power that's required for the parasitic losses, current division, matching network losses, anything. The fact that it's a Class A amplifier is 50% efficient to begin with. So yeah, all those things.
Got it. Understood. Okay, cool. So our end goal is to actually achieve that power for the second.
Yes, that's right.
Got it. Okay.
Okay. All right, so we're going to start on mixers on Wednesday then. So the mixer is our frequency translation devices. So far, we really focused primarily on amplifiers, so making the signal bigger, mitigating noise. A radio receiver has to also change the frequency of the information that we're carrying up to an RF carrier frequency and then back down in order to complete the transaction across a wireless channel. So we'll start looking at how we make a mixer. Hint, it's just a nonlinearity, well, either nonlinearity or some type of commutation, but some type of nonlinear function that we're going to mix with a linear function and end up getting a lot of different harmonics. So it's a lot like the concept of the Taylor series expansion we did when we were looking at intermod products before. fact, that's the first mixer we'll look at as kind of an intermod based mixer. Okay, so I will see you either tomorrow during office hours or on Wednesday, if not before. Have a good evening. Talk to you later.
Thank you, Professor.